Hello, I'm Injung Kim from University of Pittsburgh. I'm going to talk about our work, which is about the anatomy of the daily uses of bike sharing system in terms of elevation, distance, and seasonality. Understanding bike sharing system infrastructure is important to encourage its uses. Among diverse features that affect the system uses, we especially focus on elevation, unlike other literature works. Our work investigates how elevation variation influence the uses with descriptive analysis of daily bike trips and predictive model. In order to better understanding how the various variables related with the number of daily trips observed between two stations, we built an interpretable prediction model. We will use a Poisson regression model where the dependent variable is the number of daily trips between the directional pair of the station, and we perform the feature selection through the validation set. By using time-related, weather-related, and the urban environment-related feature, we build the classification problem, build a framework to enable prediction, and find that there is a negative correlation between altitude difference and the number of trips. Today, 55% of world population lives in urban area. Cities all over the world are struggling to maintain cost-effective and sustainable transport system. Therefore, bike sharing emerges as a solution. A bike sharing system offers a self-service, short-term, and one-way urban bicycle rental in public spaces for several target groups and with network characteristics. Bicycle uses heavily depends on the infrastructure, but most of the existing literature didn't cover the elevation differences. Therefore, we can think about what about the uses at hilly city? Is it same as the flat area? Definitely not. Therefore, we analysis in Pittsburgh bike sharing system, which is in the figure we can see that between stations there could be a lot of the altitude differences. We have three contributions. Firstly, we provide additional evidence to the bike sharing literature for the negative correlation between altitude and bike sharing uses by focusing on altitude differences in pairwise station trip. We analyze pairwise trip instead of looking at the individual stations like other literature so that we can observe the people's tendency. Second, we build and evaluate the predictive model in contrast to existing literature in the area that is mainly focusing on descriptive model. This is important since predictive model can facilitate the planning operations and examination of what-if scenarios. Third, we examine the probabilistic interpretations of the prediction with Poisson regressions, something absent from the existing literature. There are related works. In terms of operation problem, rebalancing bike from the docks with large number of bikes to the docks with a fewer number of bikes available is one of the researches. Rebalancing is a large operational cost for the system. Therefore, any improvement is beneficial. Also, there is dockless bike sharing to detect parking hotspots. There is other literature between system uses and other external factors. Weather, walkability, job accessibility have a significant effect on the bike uses. And also urban environment features such as station density, capacity, point of interest, population, and housing units are also the comparable features that affect to the system uses. There is also each station-based elevation analysis, but not the trip-based. Therefore, our trip-based pairwise altitude difference analysis is very meaningful. Our bike sharing system data is about we are getting from diverse resources. Firstly, Pittsburgh bike sharing system is a healthy ride. So we do have the trip data such as date, start time, end time, origin station ID, destination station ID, as well as station information such as station ID, latitude, longitude, and the number of dogs. We also extract the trip distance through the MapQuest bike path. For the bike distance, we do not use the harvest sign the distance between two stations, but rather take into consideration the bike street network by using MapQuest API. Also, elevation is the difference between origin station altitude and the destination station altitude. We also have using the weather data so that since it is clearly affect to the system uses. We also had a descriptive analysis of daily bike trip. Firstly, time series of daily trips. It shows the seasonality with the system uses. As we can see, during the summertime, there are lots of the uses than the winter time. Second, we also did altitude differences on average per day. So mostly downhill ride, as we can see, most of the values are negative. Even though there are some positive values, which is uphill ride, but since it happened the winter time, so the average can be very less affected than the summer. Lastly, the trip distance on average per day. So it is stable over time and less than 2 miles. It supports that the biking is a good alternative for short trip. Distribution of the station altitude differences of the trips is shown by this figure. So it mostly happens around zero altitude differences, which is plus minus 50 feet differences. This points to the absence of the linear correlation between altitude differences and the number of trips. That's the altitude differences. Therefore, we'd rather use the Poisson regression than the linear regression in the later section. The second one is distribution of the trip distance. And as we can see, most of the trips happen within 2 miles. And we also run the predictive model for daily bike trips. We built an interpretable prediction model to better understand how the variation variables related with the number of daily trips observed between two stations. Also, we use a Poisson regression where dependent variable is the number of daily trips between a directional pair of stations, and we perform the feature selection through the validation set. There are 3 different types of features, which is time-related, weather-related, and urban environmental related. For building our models, we rely on data from the last year of the operation of the system in order to avoid issues with changing patterns over 4 years of operation of the system. For the altitude difference and trip distance, range variable might be better at capturing non-linearity between altitude difference and the daily uses. We made the interaction term for the altitude difference and the distance in terms of real value and the range value so that we can see which combination has better fit for our prediction. If we see the second and third row, there is a separate season and the combined season. So which is about our data set. The separate season is each summer, and the winter seasonal data. We run these both seasonal data separately for each model. And combine the season, so we run both seasons as a one data set for one modeling. So we use the Poisson regression. Our goal is to model the number of daily trips, Yij, from station I to station J. Poisson regression essentially models the average rate of the dependent variable, which is Yij, through the linear combination of a set of independent variable x as this first formula, and we estimate the distribution for Yij as second formula. Among lateral features, we run the feature selection. For the feature selection, we randomly split the data into 3 sets: train, validation, and test, at a 7:1 ratio. Based on the result on the validation set, feature set 9 shows the lowest RMSE. Therefore, our analysis focusing on this model. Feature set 9 uses a range variable for the altitude differences and the continuous variable for the trip distance, and trains separate models for the summer and the winter. This table presents the result of our selected model. As you can see, the majority of features have the same direction for their positive and negative effect for both summer and winter season. For example, precipitation is negatively correlated with uses in both seasons. However, its effect size is different. Given the interaction term between distance and altitude difference, in order to interpret the relationship between distance and daily uses, we need to know altitude differences as well. So this figure gives us better idea how it affects to each other, depending on for each range of the altitude difference. So A plus bx, where the x is the distance, a and b are the given coefficient. This figure shows the performance on each data point on the test set. Particularly, every point on the x to the test points, which means a daily station, and the pair trip indexed by a smaller station ID and the earlier date. Y is the actual or predicted number of trips. As we can see, during the summer, the daily number of trips is larger on average than the winter. Furthermore, when comparing to the performance of our model during the different seasons, we find that the RMSE of the model on the winter test set is smaller than the summer. This can be attributed to the fact that there is less variability for the trips over the winter, since the majority of winter trips will not be recreational. Our analysis is first to consider the relative altitude difference between the origin and destination stations in bike sharing system as a factor when predicting trip likelihood. Our models are built and evaluated by narrowing down the features and analyzing an interactive way among the features. Identifying all resources or source of the elevation variation along the trip can be interesting because we only covering the origin and destination stations altitude difference. But since we don't have the route information, so that we couldn't run this information. Also, covering other hilly city and the flatter city can be also interesting. In conclusion, we explored the daily uses in terms of number of trips between directional pair of stations. Our pairwise trip analysis let us observe the riding tendency better than looking at the individual station. It can help to make a decision of improvement of bike sharing system as well as give better understanding of usage pattern. We also use the Poisson regression model and perform feature selection through the validation set. Through the feature selection, we evaluate the selected model using RMSE achieved over test set, that is about 0.16, and show its performance on each data point on test set. One benefit of our analysis is the ability to obtain an actual distribution for the prediction number of trips between two stations. The results show how altitude difference, trip distance, and weather feature impact the uses of system. And we found that there is a negative correlation between altitude difference and the number of trips. This adds evidence to the existing literature on the impact of the elevation on the bike uses. Thank you very much. Please let us know if you have any further questions.